Hello and welcome to lesson 2 of circular motion. In today's lesson we're going to be looking at centripetal force. Firstly though, just a quick recap of lesson 1. You can see that the key points are there on the screen. We looked at the radian and the definition of the radian, angular displacement and angular velocity. Just as a quick recap then, the definition of the radian, we have two radii shown on the screen, and we have an arc length in between which is also equal to that radius. Then the angle in between those two radii is equal to 1 radian. In a complete circle there are 360 degrees, but in our new method of calculation that will equal 2 pi radians. For angular displacement we had the equation theta is equal to s over r, where s is our arc length, and that's also one of the ways that we can look at the definition of the radian as well. Remember that theta has to be measured in radians. For angular velocity we had a few different equations. First one was omega is equal to v over r. We also had the equation which is more useful to you of omega is equal to 2 pi times the frequency, or 2 pi divided by the time period of orbit. Now before we move on to centripetal force itself, I just want to have a quick look at a different way of looking at the equation for omega. If we go back to basics, we know that velocity is displacement over time, or if we go even further back we can say that speed is equal to distance over time. If we consider, just like last lesson, one complete rotation of the circle, if the object starts at the top at the 12 o'clock position and goes all the way round and back to that 12 o'clock position, then the total distance it's moved is the circumference of the circle. Now the circumference of the circle is calculated by 2 pi times r. The time period, again by definition, capital T, for taking one complete rotation. In our equation here we can see now that we have 2 pi over t, and from last lesson that is how we defined, or one of the definitions and equations that we use for omega. So therefore we can say that v is equal to omega multiplied by r, and that's just a rearrangement of the equation that we had, omega is equal to v over r. So that's just an ever so slightly different way of looking at how we can calculate, or how we can justify the theory behind omega being v over r. One of the pitfalls that I see a lot of people falling into when using radians as a measurement is their calculators not being set into the correct mode. Now on a standard Casio calculator, this bit here that I've just circled, at the moment it says D, and that stands for degrees, and there are 3 different settings on there. There's D for degrees, there's R for radians, and there's G for grad, which is a unit that we don't use at all in physics. In order to make sure that our calculators are set for radians, we need to make sure that that D, well, it doesn't say a D, we need to make sure that it says R instead. Now in order to get into your calculator, first press the shift button and then press the mode button to take you into setup, and then press the number 4. That should work on most Casio calculators, and it should change that D at the top for degrees into R for radians. Now depending on whether you're doing maths, further maths, physics, or whatever combination of subjects you're doing, especially if you come to tests or exams, make sure that you check your calculator before you start using it, that it is set to the correct unit of angle measurement be that degrees or radians, and just ensure that it is the one you want, because quite often we as physics teachers see people having it in the wrong setting and therefore getting completely wildly incorrect answers. So now on to today's lesson. What we're going to do in order to look at acceleration and force that are acting on any object moving in circular motion is we're going to consider an object that starts at a point on the circle. So there's a point that I'm going to label A, and is going to move around the circle to a different point. I'm just going to choose a random point there and label that B. So our object is moving in a clockwise direction from A to B. Firstly then, we need to consider the velocity of the object at any given point. I'm going to draw on the vector for velocity at A. I'm also going to draw on the radius of the circle. One thing that you may already notice is that the velocity vector itself acts at a right angle to r. Now, going back to your maths, we know that r being the radius, if the velocity is perpendicular to that, then the velocity is acting at a tangent to the circle, 90 degrees to the radius. At B, draw the radius in, it will also be acting at a tangent to the circle, but now it will be acting in that direction there. Firstly, let's have a think about this velocity vector. We know from year one that if we have a vector, it has to be split into two components. We have to have both a magnitude and a direction. Last lesson we spoke about the fact that in our course we are only going to take omega as a constant. Well, if omega is a constant, we also know that the radius of a circle is a constant too. If it wasn't constant, then it wouldn't be a circle anymore. Well, if omega is a constant and r is a constant, then looking at our equation there, v, or at least the magnitude of v, also has to be a constant as well. Simply though, by looking at the screen and looking at what I've drawn on the screen so far, we can see that the direction of our velocity is constantly changing as it moves around the circle. Regardless of whether or not the magnitude is a constant, if one part of our vector is changing, then the vector itself is also changing. We therefore have a change in velocity. Yes, the magnitude is remaining constant, but because the direction is changing, the velocity itself has to be changing as well. We can now follow this idea through logically. If we have a changing velocity, shown by delta v, there has to be something that causes that change of velocity. Well, that change of velocity has to be caused by some form of acceleration. If we have an acceleration acting on the object, then that acceleration also has to be caused by some kind of force. In this situation, this force is acting in order to keep our object moving in a circle. It therefore has a technical name which is known as the centripetal force. A centripetal force is any force that acts to keep an object rotating in a circle. To take the two examples from last lesson, in gravity, or using gravity, we can see that the Earth is being kept around the Sun. That is acting as a centripetal force. In an atom, it's an electrostatic attraction that is keeping the electron orbiting around the nucleus of the atom. Now let's look at this force in a little bit more detail, and in order to look at that, we're actually going to look at the acceleration really in more detail and get more ideas about that. Let me first draw on a velocity vector. So here is a velocity vector. We are going to be changing that velocity with an acceleration. And if I just draw on a random acceleration vector acting at the moment what is an unknown angle. Going back to last year, we know full well that as soon as we have a vector acting at a weird angle compared to another vector, we want to split that down into two components. We want to split that down into a component acting perpendicular, and we want to split that down into a component acting parallel. So we've taken our acceleration vector and we're just looking at the two components, perpendicular and parallel, of that acceleration vector. In order to understand what's happening to the velocity, we first need to understand what each of these two vectors does and how it affects the velocity itself. Firstly, the parallel vector. The parallel vector is acting in exactly the same direction as the velocity itself, and therefore will act to change the magnitude of that velocity vector. Our perpendicular component will act to change the direction of our velocity vector. Going back to what we said earlier though, we aren't changing the magnitude. That magnitude is remaining a constant. We are only changing the direction. The only thing that we can say for certain, the first thing we can say for certain then, is that that magnitude of the parallel component of acceleration has to equal 0. In other words, there is no parallel component of acceleration changing the magnitude of our velocity vector. The only component of acceleration that we can possibly have is the perpendicular component. Coming back to our original velocity vector then, the component or the component of acceleration must be acting perpendicular to the velocity itself. Therefore, we've got one of two choices. Either the acceleration, the way we've drawn it, is acting directly up, or it's acting directly down. Now, in order to think about which one is correct, we only need to apply common sense. The object is accelerating towards the centre of the circle. There's no way of getting it from point A to point B by using this option here. This is completely rubbish, and therefore we can discount it. What we can therefore say is that the acceleration is acting towards the centre of the circle. In fact, it's acting along the radius. This acceleration then, we know, is acting towards the centre of the circle. And we can term that as a centripetal acceleration. By definition then, If the centripetal acceleration acts towards the centre of the circle, then the centripetal force must also act towards the centre of the circle as well. So we have an acceleration acting in, we must therefore have a force acting in towards the centre of the circle. So now that we've determined the direction of the acceleration, we now need to put an equation on it. This is probably one of the only equations in the entire course that I won't justify to you with some kind of derivation or some kind of theory behind it. The reason being is that the derivation itself is not required as part of our A-level course, and to be brutally honest, unless you're doing further maths, you don't yet have the mathematical ability to understand the derivation itself. For those of you who are interested, the derivation is in the AQA textbook. You are more than welcome to go and have a look at that in your own time. Here's the equation then. A is equal to v squared over r. Just a quick note on the acceleration then. You'll notice I'm using A. A is here a linear acceleration. We treat it in exactly the same way as we treated acceleration back in year 1 of the course. You'll notice that I haven't used the symbol alpha here. This is not an angular acceleration. This is a linear acceleration. It therefore takes the unit of linear acceleration, which is meters per second squared. Please make sure that you understand that this is meters per second squared and not radians per second squared. We don't study angular acceleration as part of our course this year. So A equals v squared over r is one way of looking at our equation. We will do a little bit of substitution though. We know that omega is equal to v over r. Now I'm going to rearrange this first to make v the subject, and therefore v is equal to omega r. If we square both sides of the equation, we get v squared is equal to omega squared r squared. What we can now do is substitute that v squared into our original equation for acceleration, and we get this. A is equal to omega squared r squared, there's our substitution, divided by r, which of course we haven't done anything with from the original equation. We can now see that we have r's on the top and the bottom, so one of our r's on the top is going to cancel with our r on the bottom, and what we're left with is A is equal to omega squared r. Now both of those equations, A is equal to omega squared r and A is equal to v squared over r, are exactly the same equation, just with a little bit of substitution. We can use either one. It simply depends on exactly what a question might or might not be asking us. It's up to you really to choose which is the most appropriate to your needs at that time. We can now tie all of this together into centripetal force. In order to do that, we're going to take Newton's second law, which states that the force is equal to the rate of change of momentum of an object. If we make one assumption, that mass is constant, we can then replace Newton's second law with the GCSE version of F is equal to m times A. Here the acceleration can be termed as the centripetal acceleration, and therefore F will give us our centripetal force. From the last slide, we have two different equations for acceleration. A is equal to v squared over r, or A is equal to omega squared r. And therefore, using those two different equations, we can get two slightly different versions for centripetal force. We can either say that our centripetal force is m v squared over r, or we can say that our centripetal force is m omega squared r. Just like we said on the last slide, both equations are exactly the same, just slightly different ways of working out the same thing. Now let's put this theory into practice. On the screen you can see a question. Toy train of mass 400 grams moves around a circular track of diameter 0.70 metres, completing one circuit in 10 seconds. Calculate the linear speed, the angular speed, centripetal acceleration and centripetal force. Please at this point pause the video, go and find yourself a piece of paper and attempt this question yourself. Once you've had a go, come back and I'll go through and walk you through how we can calculate all of these. So hopefully by now you've had a go at that, and let's go through how we're going to calculate it. Firstly, let's just remind ourselves exactly what we're going to be calculating. For linear speed, we are calculating v in our equations. For angular speed, we're measuring omega, centripetal acceleration measuring a, and centripetal force we're measuring f. So let's look at the linear speed first. By far the easiest way of working out the linear speed is to say that v is equal to 2 pi r over t. That's the equation that we looked at earlier. But of course here you haven't been given radius, you've been given diameter. So we can rewrite that as pi d over t. Plugging everything in therefore, we have pi multiplied by 0.7, there's your diameter, divided by 10, that's your time period given in the equation. Once you plug all that through the calculator, hopefully you should get 0.22 meters per second. I've just rounded that to two significant figures. For the second part, for the angular speed, we've got a couple of different ways that we can go about it. For the purposes of this question though, I'm going to use omega is equal to 2 pi over t. We could very easily have used omega is equal to v over r, but I'm going to avoid that because v here has been calculated and therefore has been rounded. At least we know that 2 pi and t in this situation are exact values and therefore haven't been rounded previously. Plugging numbers in then, 2 pi over 10, that gives us pi over 5, and once you plug that into the calculator and hit the S to D button, we end up with 0.63, and our unit there is radians per second. For our centripetal acceleration then, we are going to have to use a rounded value, and we can use either a is equal to v squared over r, or we can use omega squared r. It doesn't really matter which one you use. I'm going to use omega squared r, and therefore we're going to take 0.63 and square it, and we're going to multiply it by the radius. Please be careful here, you've been given diameter on purpose to try and catch you out, so our radius is 0.35. Once we plug all that in, we end up with 0.14, and our unit is meters per second squared, as we said earlier, because that is a linear acceleration. I'll leave it down to you to check with a is equal to v squared over r, to make sure that you do still get the same equation. Finally then, to work out the centripetal force, we're going to use F is equal to ma. Happy to do that because it gives us a set mass, a constant mass in the equation or in the question. Our mass is 0.4 kilograms multiplied by 0.14 is our acceleration that we just calculated, and that will give you an answer of 0.056 newtons once we've rounded, or some of you, just like me, might prefer to write that as 56 millinewtons. In summary then, we've looked at two key concepts today. We've looked at centripetal acceleration and centripetal force. First key thing to remember with both of those then is that they both act towards the centre of our circle. Because they're both acting towards the centre of the circle, they're therefore both acting perpendicular to our velocity vector. And remember that our velocity vector is acting, or is in the direction of a tangent to the circle. We then looked at a couple of equations for centripetal acceleration. We had A is equal to V squared over R, and A is equal to omega squared R. That then gave us the equations for centripetal force as F is equal to m V squared over R, or F is equal to m omega squared R.